Hey guys, today we're going to continue our discussion in chapter 1. In the first video, we talked about what is matter, and then the view that we take as chemists, matter is particulate. Today we're going to start classifying matter, and of course, what are we going to look at to classify matter? We're going to look at the particles that it's composed of. There's two ways to classify matter. We're going to classify matter by state, and we're going to classify it by composition. State is probably something you've talked about since elementary school, so we're just going to go over that very, very quickly. Composition is going to take us a little bit longer to go through, just we have some definitions to get out of the way. So classifying matter by state, solids, liquids, gases. So what we're going to look at here is how these particles are relating to one another. So how closely are they packed together? How far away are they? We're going to observe some of the properties. So do they have definite, indefinite shape? So all this information you have probably seen more times than you care, but I'll go over it quickly. Solids. Solids are going to be packed very, very tightly together. So the only motion that we're going to see is just a vibration or an oscillation around a fixed point. So they're not going to slip and slide past each other. The attraction between the molecules is very, very strong. So they're closely packed together, very strong attraction. This is going to give them a definite shape and a definite volume. So if I drop a cube into a glass, a cup, that cube is going to stay in the cube form. It's not going to take the shape of the cup. So definite shape, definite volume, and certainly cannot compress a solid. Liquids are still going to be very, very close together, but now they're free to move relative to one another. So they can kind of slip and slide past each other. Their attraction is slightly weaker than a solid, so they're still very close. They're still very attracted to one another, but there's a little bit more freedom to slip and slide, so slightly less or slightly weaker attraction. They still have a definite volume, but now we see an indefinite shape. So if I take a liquid and pour it into a glass or pour it into a cup, it's going to take the shape of that cup, right? But we cannot compress a liquid. We cannot compress a liquid, still incompressible because of that definite volume. Gases are very, 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 very far apart. So the particles of a gas are spaced very far apart. They're free to move relative to one another, and the attractions between gas particles are very, very weak. In fact, when we get to the gas chapter, we're going to ignore any interaction between the particles at all. We're going to say they're not attracted to each other at all. They've got an indefinite volume and an indefinite shape. So this means when we pour a gas into a container, it's going to take the shape of that container, and it's also going to fill up that container all the way to the top. So it's going to fill that whole space with gas particles. Because of the distance between the particles, gases are compressible. So we can push those particles a little bit closer together without changing the volume, temperature, other properties too much. So we can compress a gas. So that's solids, liquids, and gases. Hopefully that's a review from many, many years. Now what we're going to talk about is composition. So once we're finished with this discussion, we'll be able to use this flow chart here and classify our matter into one of these 4 categories that we see at the bottom. Before we can dive into those categories, we need to get some definitions out of the way. So we're going to start with matter and then make this first split here, and then make the second split after that. So the first split at the top there, we've got all matter. And when we look at that matter and we ask ourselves, is there more than one type of particle present? If the answer is no, there's only one type of particle present, that's going to be considered a pure substance. So only one type of particle is present, and the composition is invariant. So if there's one particle, it looks the same at the top as it does in the middle, as it does in the bottom. So the composition is the same throughout. If we look at something and ask ourselves, is there more than one type of particle present? And the answer is yes, there is more than one type of particle present. that would be considered a mixture. So mixture is going to be 2 or more particles, and the proportions can vary. So 2 or more particles, proportions can vary. What do we mean by proportions can vary? The example I like to use here is sweet tea. So sweet tea in the north versus sweet tea in the south. Sweet tea in the north, we've got little bit of sugar, lots and lots of tea. So is that a mixture? Well, yeah, there's tea and there's sugar present, so 2 particles, lots of tea, little sugar. Sweet tea in the south, lots and lots of sugar, lots and lots of tea. So the proportions are a little bit different. It's still a mixture. We still have sugar. We still have tea. But now it's like a 50-50 mixture rather than something else. So proportions are different, but both of those examples are still mixtures. What we're going to do now is we're going to look at pure substances, and we're going to break up pure substance into 2 more categories. And then we're going to look at mixtures, and we're going to break up mixtures into 2 more categories. So first, let's break down pure substances. So pure substance, 1 type of particle present. Can that particle that is present be broken down into something simpler? Can I do some sort of magical chemistry process and break that down into something simpler? If the answer is no, I cannot break that down into anything else, then we've got an example of an element. So an element cannot be chemically broken down into anything simpler. These are really, really easy to identify because where do we find elements? We find them on the periodic table. So we've seen 2 examples of an element already. So we looked at the aluminum can, assuming that's just aluminum. We saw a bunch of aluminum molecules stacked together. So 1 type of particle, and that particle is an aluminum atom. I can't break it down anymore. The other example of this that we saw was the helium balloon. So inside of that helium balloon, a bunch of helium atoms. Can't break helium atoms down into anything simpler. So we're looking at something. 1 particle is present. Can I do some sort of magical chemistry to break that down into something simpler? The answer is yes. I can chemically break it down. Then we see that it is a compound. So a compound is 2 or more elements that are bound together. So this one's a little bit more difficult to visualize. This one's a little bit more difficult to see. So the example that I'd like to use here for a compound is the following. Let me get my drawing tool. So what I've got here is, let's just say, a beaker of water. Okay, and I'm going to say that it's pure water, so H2O. So inside of that beaker of water, is there more than 1 type of particle present? No. From top to bottom, the only particle that is inside of that beaker is an H2O particle. So just a bunch of H2O particles. Can I break H2O down into something simpler? Well, yeah, I could do some magical chemistry and break that down into hydrogen atoms, and I could break it down into oxygen atoms. So pure substance, there's only 1 type of particle present. Compound, I could break that particle into hydrogens and oxygens. So that's an example of a compound. Now we're going to go over to the other side. We're going to talk about mixtures. So mixtures, remember, are 2 or more particles are present. When we look at a mixture, we're going to look at how uniform are those particles combined. So when I look at that mixture, can I tell where one thing starts and stops, or does it look the same from top to bottom? So if it does not look the same, so is not uniform, does not look the same from top to bottom, that's a heterogeneous mixture. So classic example of a heterogeneous mixture is salad dressing or oil and vinegar, oil and water. So if I look at salad dressing that sat in the fridge for a while, I would see the oil on top, I would see the water or the vinegar on the bottom. So I can see where one thing starts and stops. And even if I pick up that bottle of salad dressing and I give it a little shake, we will still see those little oil globules kind of all throughout that bottle. So I can still see where one thing starts and stops. So not uniform throughout. If it is uniform throughout, so the same from top to bottom, that would be a homogeneous or homogeneous mixture. So it has the same composition throughout. The example I like to use here is a cup of coffee with cream in it. So when you look at that cup of coffee, all you see is just a tan cup of liquid, right? So is it a mixture? Yeah, there's coffee present, there's cream present, probably some sugar present. But can you tell where the coffee is and the cream is and the sugar is? Well, no, it just looks like a tan cup of coffee. That's it. So that would be a composition that is uniform throughout. It looks the same from top to bottom. So here we see our flow chart. This graphic asks slightly different questions. Same idea here. So we've got all matter. Is there more than one type of particle present? Or is there one type of particle is what they ask. Yes, there's one particle. We see our pure substance, element, compound. And then over here, we see mixture, heterogeneous, homogeneous, or homogeneous. So that's it for the classifications of matter. This is certainly something you're going to see again and want to be able to practice and follow this flow chart through. The next video, we're going to start diving into atoms and subatomic particles and all the fun stuff in chemistry. I hope you guys found this helpful.